EOL, I'm pleased to introduce Dr. Lee Thornhill. Lee is a contractor with Analytical Mechanics Associates, AMA, that has worked at the NASA Langley Research Center for 25 years. He received his doctorate from Georgia Tech in atmospheric physics. Over his 25 years with NASA, he has participated in over 50 NASA field campaigns and is the PI for the NASA's AVAPS Dropsondes system and the Turbulent Air Motion Measurement System, TAMMS, which flies frequently on the NASA P3, which is where we met. Please join me in welcoming Dr. Thornhill for his seminar that's taking a first look at the inner comparisons from ARCSIX.
Hi everyone, 25 years, good Lord. My name's Lee Thornhill. So I've been NASA Langley, pretty much came on board and started finishing up our version of the wind system and have gone from there. But my two instruments were all born out here, one from Master Yoda himself here, Don, and the other from the AVAPS group. So I owe you all a lot. So we're just going to get in. So last year we were in, about this time, we went off to Greenland as part of the ARCSIX mission. And it was a 3-aircraft mission. It was basically a combined program between radiation sciences and cryospheric, that's a big word, sciences, led by Sebastian Schmidt from UC Boulder here and Patrick Taylor from NASA Langley. And we wanted to basically be able to characterize the difference in the atmosphere. We did it in 2 segments. So the first segment was during when everything was iced over, and then we waited a month and came back when everything had thawed out, and we wanted to compare and contrast the conditions. There were several buoys placed in the North Lincoln Sea that we would fly over. Found out yesterday, actually, one of them is still alive and transmitting data. The other 9 were crushed by ice, so one's still alive. So we flew out of Patuxent Space Force Base, the old Thule Air Force Base, and we basically, we did 19 flights on the P3. Let's see. The spec Learjet was up there with us. The G3 from Langley was there also. That was the remote sensing platform. And so I had instruments on the P3 for the wind system and the G3 for the Dropsondes system. And so I'm just going to kind of go over those instruments at the beginning, and then we'll talk about some of the data that we collected. This has been a work in progress when Sarah and them asked me to do this last month when I was here for the AVAPS meeting. I had one idea on what this talk was going to be, and it's evolved 3 times since then, including the last couple of days I've been at the ARCSIX science team meeting, so I keep tweaking it. So here's just sort of a background. 3 aircrafts, 175 hours on the P3, 150 hours on the G3. We had the spec plane, and I don't remember how many hours they had. It had a shorter range. And we just basically carpeted the Lincoln Sea with flight tracks and Dropsondes. And the G3 had Halo and AVAPS on there. That was our remote sensing platforms, and then I dropped Sondes from there. And then, as with most times, even like the 130 here, the P3 was instrumented with everything we could fit in it and more. It had the large aerosol group. It had DLH from Glenn Disson's group from NASA Langley, does water vapor and trace gases. It had several different types of time of flight AMS. It had an AMS. It had different particle measurements on there. And it had Elvis, that did surface elevation LiDAR. It had a little bit of everything on there. So we were up there, and as you can imagine with experiments like this, everybody had a different idea of what they wanted to do. But we think it worked out pretty well. And like I say, the science team meeting for the first one is going on right now, just down the street. And so far, some good results are coming out of it. So these are just some boilerplate slides on that I got for during ARCSIX to describe it. Like I say, the G3 did 52,000 miles, 10 flights in the spec plane. Okay, there we go. They say we completed 98% of our science scorecard. 22 different institutions, domestic and international, all combined. We flew over some ground stations. We flew over some ships during the second phase when they could actually get out there and everything was thawed out. And we did multiple coordinated 3 aircraft coordination flights. And made lots of data that we're going through. So here's my small part of this world is the turbulent air motion measurement system, which is the In-Situ system on the P3. and then the AVAPS Dropsondes system on the G3 to do the profiling and the truth measurements for the LiDAR. So just like I say, a little bit of structure of this will give some background. We'll look at some of the intercomparison work that's just starting and some of the turbulence measurements that we're making over the Nares Strait. And we just kind of go through the data. All the data that I'm presenting here is all final data. All the analysis data is brand new within the last couple of weeks. So that itself is a work in progress. So Clayton may recognize that picture there from the NCAR website, but we used the AVAPS system manufactured here. We used the NRD41, the mini Dropsondes, the newer, smaller models that did a great job. It makes multi-hertz measurements of dew point, temperature, humidity, and then all the GPS parameters such as wind speed, direction, lat, long position. Oops. Oh, that's not my phone, sorry. And then we processed it in Aspen. So during flight, I had somebody up in the air dropping them for me, then they would be downlinked down to me. I'd run them through Aspen, and then we'd upload them to GTS for real-time ingest into the forecast models. We only had one bad sonde out of 170, which is pretty darn good. We dropped 80 sondes during the first month, 90 in the second. And during the second flight, the second mission, the G3 had issues for the first couple of flights, so we only had about 5 flights with them. And so we really dropped a lot of sondes in those last flights. Yeah, they were quite tired of dropping sondes by the end of it. Thanks to Amy Solomon from NOAA and Ceres, we were able to ingest it into GTS. So here's just some examples. This is where this couple of the days that showed that it was being ingested into MERA 2. If you see, there's several green dots up on the map. All the ones up in the Arctic are the Dropsondes that we did that were ingested, and then you see some down in the Gulf. These are definitely contrasting situations weather-wise, but we were able to get them in there, and we could see some improvements in the forecast models for the next days based on ingesting some actual good observations and not just model observations. Likewise, a different day. Mission-wise statistics. So this is just showing sort of comparison and contrast between the two deployments. The wind speed definitely picked up during the summer. The wind direction changed. It was mainly out of the west. The vertical winds, they were pretty light, which is not surprising up there. There wasn't a whole lot of turbulence. There was definitely more moisture in the summer. It was pretty interesting. I went to a talk at the community center, because if you've been up to Thule/Pawtucket, there's not a whole lot of things to do after when you're not flying. And they gave a talk one day, and they were talking about birds and rain and stuff. And it was raining that day. And they said that 15 years ago, it never rained there. And now we had rains multiple times over the summer. So the climate really has changed. It's definitely warmed up there. And this is just sort of your spaghetti plots here, just showing the variability from, just during all the drops during the spring deployment. You can kind of see stuff all over the place, which is not surprising. We'd have some flights that were done nothing but looking at clouds. Some were radiation flights, so that we were anti-clouds. It's interesting, when I first started doing these measurements of all this stuff, especially the wind stuff, we avoided clouds, we avoided precipitation, we avoided icing. And then a couple of years ago, somebody's like, that would be a really good idea to fly all these forward-facing inlets into ice and snow. What's the path, worst that could happen? So we're learning now what happens. But the Dropsondes are great with this stuff. So this is the summer campaign. See the variability. One of the nice things we were able to do is the Mean Rear from NASA Langley has the HALO, the High Altitude LiDAR Observatory, which is a water vapor LiDAR, does aerosol backscattering, does a little bit of everything. It's a follow-on, if you know HSRL or HSRL2, John Hare's group at Langley. This is the next iteration of that. It's been on with me for several missions. We did CPEX together. We did some post-impacts flights together. We're on this together. And so they're able to use temperature retrieval along with their signal to get water vapor. And so we're able to compare, or he's able to compare his water vapor retrievals to what we get from the Dropsondes. And, oops. Oh, this is actually supposed to replace the previous slide, but this is another injection slide to the same thing. So this will show a few things here. You can see that the plot on the top left there is a comparison between halo and the dropsondes, and you see how well they line up. The one in the middle, we'll get to this in a little bit more description. This is a mid-latitude comparison between the dropsondes and the halo-derived water vapor, and you see how well, I mean, it's pretty much 1-to-1. You got some pictures, and if you know much about the LiDARs, they produce really great graphics and curtains of everything. So we have these from everything all over the Arctic. This is just an example slide. And these are the products that, Amin wanted me to make sure everybody knew all the products that get in there. In this case, we're really worried with the water vapor mixing ratio. Come on. There we go. So this is one of our post-impacts flights. We just like this slide because it actually shows every dropsonde what we did during this flight, how well it compared to what Amin was able to derive from his water vapor. You see the reproduction of nice small structures in there. So this is sort of a go-to slide we have often. So one of the nice things about this, or the emergent type idea, was we haven't talking a month ago, talking to Clayton, talking to Holger, there wasn't a whole lot of dropsonde data in the high Arctic. Especially we were dropping at about 12 kilometers. So when we plotted up, Brian Coster from Means Group plotted this up, and we noticed that there's a dry bias in the dropsondes when it's first launched. And talking to Holger, he's like, that doesn't surprise him. It's a time lag issue with the equilibrium from the aircraft into an extremely dry environment. So I've recently sent Holger all this data, and he's going to work on him and Mac are going to work on a correction. And we'll be able to go back and correct this data. And it's also nice for them to have this data set that they haven't had before of different spots on the planet, because it's real nice how this compares or contrasts depending on how you look at it. This is so these are the mid latitudes and the tropics, and you see because it's not so dry, we do not have those issues. This was during some of the post impacts flights versus also the CPEX flights in the tropics on the DC-8. And you can see how well everything just lines up. And that last chart that shows the dry bias, if you look at it in terms of RH, we're talking like 1% or 2%. I mean, it's very small, but it's very dry. So 1% or 2% in the high Arctic is significant because you don't have much more than that to work with. But you can kind of see, this is just another thing as a function of altitude to show that down low we match up very well, and then the dry bias takes over obviously up high. So when I processed this stuff in real time and then uploaded it to GTS, we actually cut that part out so that it wouldn't screw up any of the forecasting models. Oh, skip over this is the same idea. So going to the next instrument. It's nice to see Don here. He's the one who kind of taught me this stuff. He made this stuff up. So TAMMS is the turbulent air motion measurements. It's our version of the winds thing. That name was coined, I believe, by John Barrick long before me. And if I ever try to call it just 3D winds, he hits me on the wrist and corrects me greatly. So basically, this is if you're not used to knowing what this is about, it's not your typical, there's an instrument with an inlet out, air sucked in, and you do your business, and it's all recorded right there. So this uses pressure ports on the nose of the airplane, and we have a couple redundant probes, Rosemont 858 probes on the side that will give our angles of attack and side slip. We combine that with the ambient temperature and pressure measurements, and then you can drive the speed of the air with respect to the aircraft. Then you use an inertial navigation system. Like for this, we have an Atlantic 610. When it first started, we used the avionics off the aircraft, but I was able to get some new Atlanticses, so we use those now. That will give you the speed of the aircraft with respect to the Earth. And then it's a matter of geometry and vector addition. You subtract those two vectors, you subtract two large numbers, you get a very small number. I'll show you the equation for that. But essentially, so now in this current iteration of the P3, when I first started, there was an instrument rack about this tall as I am with cards in them about yay big that recorded either synchro, I think they were synchro resolvers, I don't quite remember what they were, A-Rank, analog, everything. Now my data system that records everything is this big. And it doesn't like the fact that I only want to record at like 1500 hertz, which I only do to get the pulse per second timing, because we don't need to record that fast. But we actually had to work with the manufacturer. It's UEI DAC out of Massachusetts. They like, we don't know why you're recording so small. I'm like, what do I need more data than that for? But so that's where we've kind of, you know, made great strides throughout the years. And the equation, would you like to talk about the equation?
I'll leave it to you.
Okay. So it's very long, but it basically does a coordinate transformation and adjusts from the aircraft angle to Cartesian coordinates, and it takes all the correction for pitch and roll, and your side slip and your true airspeed, side slip, and angle of attack, and so it subtracts the platform motion of the aircraft minus the speed of the air with respect to the aircraft. So you get two big numbers. You subtract them, you get what should be a very small number, except for, you know, like in storms and updrafts and stuff. And if you're flying straight and level, you can approximate it by the speed of the aircraft, the vertical, you know, the vertical velocity of the aircraft minus the true airspeed times the sine of the pitch minus the angle of attack. That will get you there as an approximation for straight and level flight. So if you are familiar with the program Igor, I do all my programming in Igor. I know just enough Python programming to get me in trouble, so I really try to avoid it. This is an example of some of my software of what we look at. This was from impacts, flying out of Wallops into East Coast winter storms and back home. And you can see the vertical winds, the right vertical winds up top, and you can see when we take off, it's nice and calm, and then it's not for the entire flight of the mission until we dip out of the storm, we dip below the storm, we're back in, you can see all the vertical motion, and then when we return, it starts to calm down again. So I kind of have software like this for each of the flight missions. I didn't have one. I have it for ARCSIX, but ARCSIX was, in comparison, very boring. There's hardly any turbulence except when we were down low. So it's like looking at a flat line, which isn't that exciting. But, you know, I kind of like, if done correctly, the mean vertical wind over an extended distance in the absence of storms should be zero or very near zero. So it's a good idea to make sure your calibrations and everything are correct. And this is my sanity check for different straight and level altitudes from flight to flight. This slide, oops. These next couple slides did not translate well from PC to Mac. But these are calibrations. So you have to do a lot of calibrations with the wind system, and it's very, very sensitive. You do different speeds. You hold straight and level to get your angle of attack, slope, and offset, which will help you derive your vertical winds. There is tail wags, which basically imagine you're flying, you're holding your wings level, and then you crab left to right in sort of a periodic motion. That will give you your slope for your side slip angle. And then there's reverse headings. If you pick a path that's along the wind, fly into it and back, you can start to figure out how to characterize your pressure deficit or defect, which is basically the change in for what the ambient pressure is versus where you're recording it on the aircraft. Different places on the aircraft, the air is greater or less. So we've done all that, and then the crosstrack to the wind will give you your offset and your heading, your inertial navigation system, which since mine's in the Planix that belongs to me, it's put on the airplane all the time. It's not surveyed in, but it's very important that you get it correct, because here it's a very small thing, and I don't have my glasses on, but you can get a couple meter per second change in your mean wind based on direction if you're off by a couple tenths of a degree for a side slip, for your heading offset. So it's a very sensitive thing, and then you have to redo this over and over again because there's natural variability in the wind. You try to go into nice, homogeneous, clean airspace, but that it doesn't usually work like a textbook. So you do this over again to compile statistics. And these are actually these little plots that initially were much bigger shows the speed variation. So it shows our calibration results between since Oracle's, CampX, Impacts, and then ARCSIX. Everything lines up great. Same thing for the side slip angle. We just keep compiling statistics, and we don't do them. A lot of groups will ask to do those every flight. That will really tick off everybody else doing science because people don't want their lidars and stuff shaking around. We do it several times during the mission or try to get a flight dedicated just that. so that we can keep a sanity check and make sure everything is going well. And this is the one I'm going to send this slide to Chris. So we did this, and one of the things we kind of noticed on impacts was the angle of attack offset. If you just change it slightly, like a few tenths, a few hundredths of a degree, it'll change your baseline from your vertical winds. And one of the things we were noticing was I get nice histograms, but the mean would be off. And we discovered there's a little bit of a pressure altitude or impact pressure. All these terms go into the same equations. A dependence that we noticed during impacts that we were able to start to incorporate. And like Chris and I talked about this several times, where I don't have a complete handle on exactly what it is, but we're playing with it in correction. I think I ultimately ended up for ARCSIX, I ended up making it as a function of impact pressure that just slightly tweaked the offset. And what was in those blank spaces right there were 3 plots that basically showed how without the correction term, the first correction term, the winds were all over the place. The second one, they had nice distributions. And the third one, they all lined up right on top of each other when you applied that secondary offset. And if you're doing flux measurements or something like that, a lot of times you'll detrend the data or demean it. So a slight offset won't really impact you. But if you're not really familiar with the data and the accuracy and stuff like that, precision, and you see that your mean wind is 0.12 meters per second, then I'm getting calls like, why is this off? And it's probably really not. It's just because it's a very sensitive offset. So we've been able, as the years go by, we've gotten much better at correcting those out of it. So one of the things that we're often asked is another way of the calibration. So if you're flying and using the avionics of an airplane and you fly out in one direction, you'll get a wind speed and direction. If you turn around on that same ground path, ground track, they're going to tell you the wind speed and direction is different. It's really not. For all intents and purposes, it's not. But this is the differences that go into correcting the winds like this versus just using the heading and the heading and stuff that the aircraft uses geometry to compute the winds. So in this case, we flew out to do, this is a radiation flight, so this was a cloud-free, about as nice as days you're going to get up in the upper Arctic. We flew out, and we flew basically in every different direction. And the winds were all the Dropsondes showed that the winds were all out of in the same direction, well, basically just out of the north in this case. And so this is a sanity check for us. The wind speeds changed a lot, which there's natural variability. That's not surprising. But regardless of where we went, the wind direction stayed relatively constant within reason. So it's a good sanity check that we have the calibrations, in there correctly. Now I mentioned, I got a few more on these and then we'll get to some fun data. If I can figure out the slide here. Okay, I mentioned icing. Our temperature sensor is non-de-iced. That way we'll get a faster response out of it, somewhere between 5 to 7 hertz if you're doing turbulence statistics. The problem is when you fly into ice, it turns into a snow cone. And there's oftentimes during ARCSIX that we'd run into icing. Nothing as bad as we did during impacts because we'd eventually fly out of it and it would dry out and we'd be back in business. But this is a good example of it, the top right plane here, top right figure. That the red trace is the temperature from the aircraft. It's not calibrated. The blue is ours data, and you can kind of see that they're tracing along pretty well. And then there's a shift, and our data looks completely different. And then after a while, it dries out, and we're back in business. Our temperature sensors were calibrated right before the mission and right afterwards. So we have a good idea of what the temperature is for our total air temperature probe. So what we ended up doing in order to be able to compute winds during that time was I tied the aircraft temperature to our temperature, and that's the plot on the bottom left there. We'll not get the response because it's basically once or twice a second. So we won't be able to get any fast turbulence data during that time, but anybody interested in the mean winds can still get their data from it. And also DLH, Glenn Diskin's water vapor group, they use our temperature and pressure data in order to derive their data. So we don't like that. We try not to have gaps. I mean, there are times in the data when there's gaps. That's just it's the way it goes. We also had some icing issues with the radome is not heated, so you can't heat the radome, so we'd have some icing there. And then our 858 probes, the angle of attack one was heated. The side slip one used to be heated, it died out. Those are old probes. So we lost some data that way too, but we have, all the time, for all the icing we went through, we actually were able to retrieve a lot of the data. So now let's talk about some of the data. This next few slides were completely off my radar when I first thought about what I was going to do for this talk, but I started playing with it for this in the science team meeting, and this actually turned out to be really, really neat and interesting. So Patuffik is down, Patufik's down here where the star is. So the plane would go into Lincoln Sea, and then 8 times during the flight, they would come down the Nares Strait. And the wind, basically due to the geography and the weather patterns up there, the wind is funneled down that strait, and there are several times when it really gets channeled together. So there was, I think the first flight was pretty, were you on that one? Yeah, I wasn't on any of them. She was on there. It was very turbulent, and to the point where the pilots are like, we can't stay down here for multiple hours. We really need to go up and take a break. If not for you all, for us. And so they did this, they repeated this several times. And this wind actually will help create the polynyas that we are after and looking at down in the Keene Basin. And so it's all, due to that. So we wanted to characterize, we wanted to see in the beginning, what's it look like all ice, then as the ice starts to melt, and then when it's open water for the polynyas. So we wanted to be able to characterize that. And so they weren't really looking at it in terms of winds and turbulence statistics, but since this is what I do, I thought it would be a pretty cool idea. And actually the ARCSIX people haven't seen these slides. I think I might talk for those ones tomorrow. So for the Nares Straits, like I say, we did 8 of them. Sometimes we did sawtooth patterns where we just kind of went up and down and up and down. That is not as exciting for the vertical winds. But we did, when we went low and we stayed low, you can kind of see the winds, the turbulence pick up. This spot right here is about where we entered the Nares Strait, so you can see that the wind speed really picks up once we get in there, and then starts to calm down as we get further down the strait. So some of the fluxes we want to do, sensible heat flux, we can look at the flux due to heat. The latent heat flux I used a fast, DLH produces a fast water vapor, so I got a 20 hertz file for that to match up to the wind data. So we can look at fluxes of that, or we can look at mechanical energy flux, which is a momentum flux that uses the vertical winds and the horizontal winds. And so what I wanted to do was, you need to make sure that your turbulence data looks right. You don't have any noise in your signal. And our data, it should fall off, greater than 1 hertz, it should fall off at about a -5/3 slope, which ours does. So that if it rolled out, we'd see we'd had a noise flooring, or if it had spikes, there'd be noise sources. Luckily for this, knock on wood, we don't have any of those. And if you want to look at fluxes, you can do W prime, T prime will give you your heat flux. W prime, Q prime will give you your moisture flux. And depending on how long a segment you get, you can find out what wavelengths are involved in it. This is, for instance, a sample picture from CampX, and it showed that there was some small scale flux, but mainly it was all kind of larger scale motion that contributed to the flux. And working with Glenn Wolf's group up at Goddard, him and I have kind of settled on over 50% overlapping segments, because if you pick a time period, let's say it's 5 minutes, which I think is what I use for this later analysis. If you just arbitrarily take every 5 minutes, there could be times when right on that interface where there's really something important but your arbitrariness of picking times, you're gonna miss it. So if you do a 50% overlap, you're kind of more likely to catch all the features that you really want to see. So I wrote some code up to do this. And like I say, talking about scales of influence, the top plots show it's an eye chart there, I know, but you can see a lot of the little wiggles in the vertical wind also matches up with the little wiggles in the water vapor and the temperature, showing that there's transport at small scales. Down low, that it's really impacted by your eyes are immediately drawn to those waves in the middle. It's more mesoscale or synoptic scale transport that will lead to the flux measurements, because that will dominate. We don't really that's kind of outside what I really do. I don't care about the longer, the more synoptics deal, we're really looking at the turbulence flux. But both of them will impact your flux measurements. So this is one of the near straight runs. A, B, C, and D will correspond to pictures here in a little bit of solid ice, some open ice with leads in it, ice again, and then the polynya. And you can kind of see it in the latent heat flux there. Where A is, the latent heat flux is very small. We get over some open water, and all of a sudden it increases up. The surface freezes back over to solid ice. It's back to zero. We get over the polynyas and over the open water, and then all of a sudden there's flux measurements again. So from the flight video that I got from INSERC, you can actually see this. Is kind of hard to see. It looks like fog, but that's really just low sun angle and solid ice for A and C. You see some cracks of the ice over B, and then D over this huge, big, nice polynya. So you can, so the flux, you can definitely, the flux that we measure compares nicely with what we're actually seeing out of the aircraft. There's some conversion problem between EOL to PC to Mac that I didn't know till today. But you can kind of see that when this gray line here is when we get over the open water, and all of a sudden when we're over the ice and we're over some of the open leads, you can see some flux, but you can see a huge difference. It flips a sign when we get over the open water. So there's actually, it makes sense that it would be more flux there. Same thing with the latent heat flux. You can see much more contribution when we're actually over the open water and much less when we're over the ice, which is what we'd expect. And in complete transparency here, this is all new analysis. We haven't really quite tweaked out we know our time lag's within a sample or two at 20 hertz, but we haven't completely optimized it for the time lag analysis yet. Okay, so now what I initially said I was going to do at the beginning of this talk. We have some opportunities. We sort of did something like our Mean Solutions group, some of his grad students wrote some papers comparing the TAMMS data, the wind data with the Dropsondes data, and they also did with the HSRL2 data. But this is a case that I'm going to kind of look at doing the similar idea, though differently, for the data up in the Arctic. So the red lines are the flight path in the P3, and then you can see the blue dots is where the G3 Dropsondes. So we were I've started looking at what's the best way to compare this, because we're not doing profiles in the P3. We're generally flying straight and level. Every once in a while we'll get lucky and we'll be out in the middle of a sawtooth or something like that when the sun comes by. So how much can we really compare? The sun doesn't drop right next to where we are in the airplane. That's obviously a safety issue. So there's a distance issue. So what can we actually see from the data is really what we want to see going in here. So this is just one of the examples from the third science flight. You can kind of see, we went up here, this is the radiation flight, so there's very little clouds, and they drop signs all along this path there. And we catch various little segments between the P3 and the Dropsondes. And you see at first glance, looking at it initially, we compare very well the Dropsondes and the wind data, the TAMMS data, and the pressure, temperature, and everything. So first, these have been off, we've just done this in the last week. So at first glance, we're comparing very well. The problem is as I've been playing around with it, this chart here is very misleading. Yes, this is exactly what the Dropsonde did during that time from 50, during those times. But the P3 wasn't right there. P3 was somewhere else. So I've changed this to a latitude, longitude thing in order to try to figure out what's the best way to really get them close. But we've done this for a few flights. And you can kind of see just various times. This is one where we just stayed down low the whole time. And we match up, temperature we match up really well. And the winds are kind of all over the place because there was multiple suns there. And this was a cloudy day, so we're in and out of clouds all the time, so the dynamics and regimes are changing. But all in all, at first glance, we're comparing very well between the TAMMS on the P3 and the G3 Dropsondes. I'll repeat this for a couple. let's get to the, you can just see in different situations, we were matching up pretty well. So then I started looking, I was like, okay, well, that's all great, but let's see if we can actually do this a better job. So this is just the first day we dropped sondes, we dropped 9 sondes. So I was really interested in, during the time of the sonde, so the sonde drops here to there, what is the P3 doing? Can we actually look for times when there's actually an altitude change enough to actually be able to get more than a point on a profile to make something way more interesting? And this is sort of where we're evolving the last couple of days when I've been at the science team meeting. So you can kind of see here, this is a little confusing chart, but the dropsonde came down. The blue line here is the altitude of the P3 during this time of the dropsonde. So now I've been adding time onto both sides to try to figure out what's the best way to get close to the dropsonde, whether it be time or space or what have you. But this is the one where if we start to add time, all of a sudden we're starting to get closer to where the dropsonde actually drops. So from this, we can start to decide what is more important. Is it, how long can the dropsonde be deployed and dropped before we get there when we're still comparing apples to apples? On a radiation flight, that shouldn't be much of a problem because the situation wouldn't change that much. If you got wind and you got clouds, then all bets are off because things are advecting through there. But you see in this case, we match up really well with the winds, the temperature, the pressure. So this is a promising start, but I'm still kind of throwing things against the wall to see what sticks for the analysis idea. And similarly, this is another flight. You can see we never, the comparisons are somewhat okay, but if you look at the winds, we're at best we're close when we're too far away. The distances just don't really compare. So we got to figure out what is that sweet spot that we can still compare up to a certain distance away and find out that we're actually still doing something reasonable. So summing up, I guess I went through this faster than I planned. The data sets are final. The analysis is anything but, it's just preliminary. We're learning this stuff as we go. Like I say, I worked with Holger and Clayton and them in the AVAPS group. We want to try to get that dry bias correction into the archive so that people can use it. And we want to pull in some of the Merit 2 data that we can continue to use another comparison. I started this for oracles, and I never got far enough in it to get the paper written. I got several of those waiting one of these days. So the comparison analysis is evolving. It's completely up in the air right now. It'd be nice to get a paper out on this the near straight analysis and on this comparison between the TAMMS and the AVAPS data, and also compare it to what they did during the activate for the same sensors. And shout outs to the people who dropped the Dropsondes for me, and to the Langley pilots and maintainers. Same thing with the Wallops maintainers for the P3, and Glenn Diskin for his DLH data, and Ryan Bennett from Insert for the video data. And that's all I have. In my head, this was going to be 47 minutes.
Thanks,
It did
Lee.
not make it.
It's preliminary, but it's fun to see the analyses starting to come out and see the actual comparisons between the data.
It's actually nice to have time to do it. I've done, I did ARCSIX last year, the year before, plus SARP. So that was about 4 months of my life. The year before that, I did 3 projects. I've been averaging like 3 field projects a year for like the last 15 years. So I've not had time to actually look at data. And this year, despite all the weirdness that is this year, was actually an overlap year anyway, so I'm home to work on data. So it's been kind of nice to actually have time to actually sit down and look at data and try to figure out what I'm doing as I'm going. So
Yeah, that's great.
what are you talking into?
This is our tossable mic, which, speaking of, does anyone in the room have questions?
Hey, Lee, great presentation. It's
Thanks.
great to see the drops on data and some good comparisons. I'm Terry Hoax, that's my whole program.
Oh, hi, Terry. We've
Yeah.
talked many times, but not
Yeah,
in
and I'm
person.
sure Holger asked you this question more than once, but you guys did do the RH dry bias regeneration
Yes.
for the drops?
Yep, prior to every
Okay.
flight.
All right, thank you for doing that. That makes a big difference.
Yeah.
So that's great to see. And I had another question, and now I forgot what it was. So
You
it'll
just,
come
want
back.
us to,
So-
you just want us to throw the mic back at you.
Exactly. It'll come back.
Yeah, as soon as I was at the meeting last month, and yeah, we missed you there. As soon as I showed up to Holger, he's like, "Oh yeah, I know that is." I'm like, "Of course you do." So
That's why we have Holger.
yeah,
Any other questions?
I had one question. You showed some comparisons between the Halo
Yes.
and the early on in your talk. And I was curious about the flight paths. Do they follow a drop zone down or up? Or
no, they stay at pretty much 12 kilometers, and then they just stay the whole time up there. Let's see.
But the profiles were for a whole altitude range.
What's a LiDAR?
Oh,
Yeah, Halo's a LiDAR, so.
oh, okay.
Yeah.
I'm thinking about the Halo aircraft. It's good.
Oh, yeah, no.
Okay, good. Okay, that makes much more sense. I was thinking, man, that's one heck of a flight path. Have you ever compared your in-situ wind system with either Halo or the other aircraft?
With what?
With the German aircraft?
I have not. I've compared it with yours.
Okay.
I wrote a paper on it in let's not go back that far.
I won't go.
A long time ago.
Okay, because I know they have a different way of calibrating.
They do, yeah.
Their system.
Yeah, I think they do a lot of box pattern stuff too, I think.
Yeah.
And yeah, no, we've talked about it, but we've never actually done it.
Okay. Have you ever thought about maybe getting together a conference or a workshop just amongst folks that do this kind of thing?
No, honestly.
Kind of a fun
It sounds like a great idea, but it's never, yeah. Because there's not that many of us. We wouldn't need a big room.
Yeah, I
Yeah.
mean, there'd be room here for it.
Yeah, like I've been down and talked to Chris and stuff, and we've gone over things, and
Cool.
yeah.
Thank you.
You're welcome.
Did you remember, Terry?
I did, but if there are other questions, they can go before me.
I don't see any hands jumping up.
Uh-oh.
Sorry.
You have to toss it. I wanted to show off my prowess in catching a ball. Yeah, I'm just curious, is there any effort in NASA to develop any new kind of technology for air motion measurement, like laser or anything, laser, Doppler laser system or anything like that?
Well, yes and no. There's no direct funded idea. Amin and I are tossing around trying to get winds out of his Halo thing. There's there's AWP, or what used to be called Dawn, but they don't do flight level winds. It's a wind LiDAR. But Amin and I have been tossing around ideas on how to do this using his stuff. But like the old, it was before me, John did an SBIR for Coherent Technologies Group, I think it was, that you try to do like laser, like the out in front of the aircraft laser thing, that at least from the NASA point of view never went anywhere. So I do know, I don't know how much, I mean, I assume I can say it, I'm gonna say it, just not, I'll blame somebody else. There's some SBIR things out in order to do an improved static air temperature measurement to get something that's faster. You know, it's interesting, like when we first met, we were using the Lyman alpha hygrometer data, you know, and then they stopped making those. And then not until Glenn has the DLH have we gotten a fast water vapor measurement again. There hasn't been a lot of advances, you know, like the 858 probes, we were lucky. I mean, prior to impacts, we never wanted to go through clouds or anything. So the fact that our heaters didn't work, we didn't even know because we never hooked them up. And then Jerry Heinsfeld got me onto impacts, and he's like, "We're going to fly through icing." I'm like, "Oh, that's really a bad idea." And so we hooked it up, and sure enough, the angle of attack one was great. It worked. The side slip one did not work, and they don't make them anymore. But they do. Rosemont went to somebody else, which the Collins, and I don't know what their name is now. They're like 3 companies down the road. There is an 858 HB that they make for a Japanese strike fighter that is exactly looks like a stunted 858 Y probe that we used to use. So we've gotten some of those, and we want to, and when things settle down some, we want to try to test those out. They have heating capability, they have everything, but like I say, they're closer to the fuselage, so we're not sure if we're going to have to put some type of offset or something like that. But outside stuff like that, there hasn't been great advances. There's advances with data recording, but the fidelity of the signal as itself, it's sadly kind of been behind. You know, one of the things you kind of notice is people are like, oh, it's a wind measurement, and then you see the full equation, and they're
Yeah,
like,
make a sounding.
that's a lot of stuff. You got to go long.
Good pass. I could ask you so many questions. But anyway, I'm going to ask some real simple questions. Even though you've been saying you've been very busy with many field programs, but for NASA and the Dropsondes system, anything in the near future?
Yes, so next year, yeah, in 26 we're doing, it's called Nurture. It's an upper tropospheric, low stratospheric experiment. It's actually going to be the first experiment on the 777. But the year before on the G3, we're going to go do a dry run up in northern Canada. So that's the next time we're doing, that's the next time the system will be on there. I'm now pushing to get the new AVAPS system. Needless to say, we're kind of waiting to see how things play out. But you know, because I saw it during the workshop. And then in 27, we're doing the full workup on the 777. So we'll be dropping sondes there as well.
Good.
So.
Good to hear.
Yeah. So yeah.
You answered my other question because we have the new system that you really want.
Yes. Did you bring me one?
Yeah, it's over there.
Okay, cool.
It's gift wrapped.
All right.
Yeah. The other, just kind of a curiosity, because I've been like on many NASA programs with like Jerry Heimsfield, all the other instruments on Global Hawk. And it's very interesting when you look at the different LiDAR systems and the Dropsondes systems, comparing all the data. And from a science perspective, it's always really very clear that you need everything.
Yes.
Because they're really doing different stuff. But I'm just kind of curious, your perspective, more from a science perspective in terms of needs, because when we look at the LiDARs, it's a very nice continuous operations, continuous measurements, drops on single point, single instant in space. How would you kind of scientifically, putting on your science hat, kind of talk about the value of both?
It depends on your regime, right? When we did oracles, you could fly for hours and nothing changed. The clouds were the same height. It was the same visibility. The results all looked the same. If you had that, you could do a dropsonde at the beginning and end and a couple of LiDAR curtains and you had everything. If you do something like Activate, where you're flying in and out of these little puffy clouds that will basically disappear within an hour and nothing looks the same from 1 minute to the next, LiDARs are great. Dropsondes, I think, are better, but you can't keep dropping them. There was some, and that keeps getting increased. Who was it during the meeting, Clay? There's somebody that wanted to be able to drop like multiple sondes like a second.
Is that Joe?
Hurricane,
Yeah.
Right, Joe Cione.
Yeah, and I mean, you could fit enough in the 777 to do that, but you couldn't afford then any flight time. It's interesting because dropsondes are expensive, but what's the cost to design a LiDAR and build it? You can buy a lot of sondes for that. So it's a balancing act, but in all honesty, dropsondes the LiDARs make really pretty pictures that people outside the community really like the look of. They're bright and colorful, but like Amin can't do what he does without our dropsonde data to validate what he does. There's satellite, whether it be satellites, this will get me out. I had to take off my In-Situ measurement person hat for a second. You have to tweak LiDAR data. Your LiDAR retrieval has tweaks in it in order to, you need the truth of the dropsonde in order to tune your LiDAR. I mean, I've learned this from, Amin and I have been in the tropics, we've been in the mid-latitudes, now we've been in Greenland, and he tunes his LiDAR based on where he is, there's nothing wrong with that. That's the way it works. But you have to start somewhere. Your base principle or whatever, your base profile is the dropsonde. So it's very valuable and it's interesting. So obviously I knew what dropsondes were, but prior to CampX, when NASA got the dropsonde system and then we inherited it after that, I'm not sure I'd been on a field mission that had dropsondes. And since then, I haven't been on a field mission that doesn't have them. You know, it's like they realized, oh, look, these things exist. They're great. Maybe we should try them. So now they're invaluable. You know, and we did remote sensing. We've done remote sensing projects for, you know, years and decades. And it's really nice to be able to tie it in. You know, one of the interesting things, talking about the different types of LiDARs, you know, there's one that just does wind. There's one that does water vapor. There's one that does aerosol backscattering. So everything has its purpose, but you have to have the Dropsondes to you know, tie everything together. But it really goes back to how messy is the environment you're flying through, you know, and then you have to figure out how to tune it all, you know, because like the paper from Activate was the first version of it compared the winds data from the AVAPS with the retrieved surface winds and lower level winds from HSRL2. And some of the first questions I get, well, why didn't your TAMMS data look as good? Well, A, I'm not in a mixed layer. You know, I'm up in the atmosphere, and the distances they were comparing them to were much shorter. And the further you get away, the worse the agreement is. You know, if you can make the argument that the atmosphere you're sampling 200 kilometers away is the same as the one you're doing here, why are you flying so much? Just take a couple points and you got everything. But the environments that we like to fly through now are so heterogeneous, you have to really figure out a good sampling strategy, or else you've missed trying to tie everything back together. That's my opinion on it. You know, my first field mission was Tropics B in '98, I think. And all we did was fly into nothing. It was background remote Pacific air off Christmas Island. And we were doing nothing but measuring background, you know, which is very valuable. You need to know stuff like that. For something like that, I'm not sure you need a LiDARs, you just need a couple of Dropsondes because nothing was changing. You know, when you do Activate, you need everything.
Very good. A lot of stuff for thought.
Yeah.
So Bart Geertz has a follow-up to Jeff's question.
Okay.
It would be good to see a comparison between a TAMMS and a small gust probe like an Ames 20 that's out on the wing. The question is about aircraft downwash, flow deformation. I think there was an Ames on the Learjet. Did you guys do any parallel flights?
No, but this summer I've gotten funded to put a new version of TAMMS on the Dynamic Aviation B200. We've been doing SARP missions and Carafe and what was the other one we did on Blue Flux? We were looking at flux emissions over mangroves. The next iteration of that, assuming everything goes well, is Farm Flux. And for SARP this summer, we're going to do the first time of flying the TAMMS system on the B200. We also have an Ames 20 on there. So there will be a paper come out of that to compare the two.
Nice. We'll stay tuned for that one.
Yeah.
Are there any other questions? You just want to see me attempt to toss it that far.
Thank you. I just had a question on this, the sampling rate on the TAMMS on the various pressure sensors. And are the pressure sensors right up against the sampling holes, or is there tubing?
There is a small length of tubing. For the radome, it's about 5 feet or so. It's wherever the depth of the radome on the P3 is. The 858s, it's just a couple inches. So there's just basically a fitting between the sensors and the transducers and the 858 probe.
And what's the sampling rate of the transducers?
So they're the side slip ones are Honeywell PPT2s, and I think I got them at like 1,000 hertz, way overkill. But I just went ahead and did them up for the one. The other ones are Rosemont, and I think I sample them both at 1,000 hertz, but then I average it down. I really honestly, if I didn't have the pulse per second stuff, I'd do it like 100 hertz. I don't need it that fast, but I can't measure one signal really super quick and the other one's slower. They don't have that technology. So in order to be able to do time lag stuff with DLH, I completely oversampled it.
Thanks.
All right. Any other questions? All right, I don't see any more online. Lee is here through tomorrow, right? Otherwise, feel free to reach out to him with questions. Let's thank him one more time.
Thank you.